Hello, everyone, and welcome to the GeekNarrator podcast. I'm your host, Kaivalya Apte, and today I have another interesting topic and a very special guest to discuss that. Today we are going to show you how to invest in Bitcoin, how to earn more money, and how to become rich. Okay, I'm just kidding because we are not finance folks. We are engineers. We focus on technical parts. So we are going to talk about Bitcoin, but more from technical perspective. Basically, what we are going to do is read the Bitcoin white paper and share details, share some insights and concepts, and give you more ideas around what it means, what different things mean in the world of Bitcoin. Um, this episode, we are also trying to demonstrate how we um try to read white papers and how we approach white papers and how it can be helpful for you. So, with this, I want to welcome Arpit Bhayani, who is our first repeat guest. So, thanks for thanks for that.
Thanks.
And
Thanks,
so, yeah,
Kaivalya.
let's start with a little bit of introduction, and then we can get started.
Okay, so a bit of introduction about me. Hi, folks. So, folks who are listening me again, so you already know me, but still a very quick intro from my end. Hi, folks. My name is Arpit. What I do is I run a YouTube channel named Asli Engineering. Translated to English, being it means basically real engineering, where I share deep tech topics. I try to cover the core engineering topics that no one talks about. Few things that I covered: hash table internals, BitTorrent internals. I dive deeper into basically how entire this particular P2P network works, how the distributed hash table works, and all of that. So all in all, a full geeky, nerdy thing is what you'll find on my channel. And really excited to talk about Bitcoin. I've never invested a single penny in Bitcoin, but I just love the engineering behind it. So from that perspective, I just love this paper. So like really happy to talk to you through that.
Awesome, awesome. Yes, and we also did a podcast earlier, which was focusing mainly on fault tolerance and scalability. So do watch that episode as well if you haven't. But after you watch this episode, so okay, let's start with the basic question that I have seen many people or many folks comment on your post as well. Whenever you post something about white papers, people also reach out to me sometimes about white papers. Should we read white papers? How do we approach white papers? What do we get out of white papers and all that? So let's address that first. Uh, what do you think, in your view, who should read white papers, and what should one expect to get from white papers?
So, what I feel about white papers specifically is anyone who has time to read should read white papers. White papers are very dense, but that's what but basically that is exactly what the highlight of that is. Because they are dense, you'll find a lot of information just very subtly explained in one word, one line, one phrase. But when you go through that, because they're very information dense, you'll be you'll be touching upon a lot of depth topics. So it's easy to build shallow knowledge, but when you want to dive deeper into something, white papers are the best source of information. Plus, after a certain stage in your career, the information, like say when you're early in your career, you will find information in blogs, you'll find information in, let's say, YouTube videos. But after a certain stage, the real information, the big problems are solved in academia. You'll find papers about it. So that is
Yeah.
where to dive deeper and get very deep understanding of that subject, topic, problem statement. That's where white papers would be extremely helpful. So that's where you should be reading it. But I've personally started reading white papers since college time. I'm obviously not as exhaustive as what I do today, but at least one paper a quarter, a month, something like that. During my masters, I read a ton of them, and then it basically forms a habit around reading them.
Yeah, yeah, that makes a lot of sense, and that is actually spot on. So white papers can give you certain ideas, some concepts, some pointers, but at the end, what I feel is you have to still probe further. You have to be curious, and you have to do a lot of other work as well to completely get the idea of the white paper, because white paper is limited in number of pages, and they can't just go like 100 pages or something. So so as this white paper we see here, Bitcoin, it's like 8 or 9 pages. It is so dense. It is like filled with concepts that are complicated to understand, also implement. but it's so precise and also concise in manner it is presented. So this white paper came in 2008 and was published by Satoshi Nakamoto. No one really knows who they are. He, she, who. No one knows. And but yeah, it's an amazing white paper. And let's get started.
Yeah.
So um, let's go with a brief abstract, like what this
Hmm.
white paper is about, what
Hmm.
we are going to read today. Let's start with the abstract.
Okay. Just to add to a line, any white paper, like any and every white paper, never spoon feeds, which means that it would never give away the heart and soul of it. What it
Yeah,
would do is it would just present you an outline. Implementation is up to us, but that's what the best part is because it never spoon feeds. It makes you think. And this Bitcoin paper, when I was reading it the first time, I thought, hey, it's pretty simple. But when I read it a second time, it was like, oh my God, he just mentioned Markle trees that we will be covering in some time in just one line and expects us
yeah,
to know what to do with that. And
yeah,
basically that's the beauty of any and every dense white paper that exists. Right?
yeah,
Okay. So let's start with the brief abstract. The abstract itself is really interesting over here. So what it says is it's a purely like this paper would present a pure P2P version of electronic cash.
yeah,
Now, to highlight onto this problem is that from real world perspective, if I take that, in real world we have basically physical currency. When we have physical currency, I have this unique particular currency note, and if I want to purchase something, I can just take this note and I can basically physically hand it over to you. When I do that, this unique note that used to belong to me now belongs to you. That is an
yeah,
easy problem. Like you literally physically moved this value from my pocket to your pocket, right? Now this one note that I physically have it is unique. No one else has this note, right?
yeah,
This how our basically this is how our entire physical system works. The entire market value works.
yeah,
What this paper tries to do is what it proposes is a P2P version of electronic cash that would allow online payments to be sent directly from one party to another without going through a financial institution. So right now when we are transacting online, what happens is we transact amount through a bank, which is a financial institution. So here bank is acting as a central entity. So we
yeah,
tell the bank, hey, I want to transfer monies to let's say Kavela's account, and I would like my money would be deducted. And when they say my money is deducted, it's from the bank account it is getting deducted, and in your bank account it is getting added. So bank
yeah,
is acting as a source of truth. The problem here is if I would want to do this entire P2P, which means that I don't want banks to be involved at all. I want to digitally send money from my account to your account. And it's not bank account we're talking about, from me to you, literally. Now, how do we do that? So this is what the idea of an electronic cash is. Right? So some kind of tokens that we now basically typically call it, like some kind of tokens that we have, some kind of coins that we have, that I want to transfer it from me to you. Right? Now this is the
yeah,
problem. Now why is this a problem? This is where it adds the problem of double spending. Now, because
yeah,
it's a pure electronic cash, there is no bank involved. So, what's stopping me from? I have some money with me, some tokens. I because it is electronic. What's stopping me from not to double spend it? So, for example, if I have two users, let's say first is Kevin and let's say some other friend ABC. What's stopping me to not send this digital copy or rather this digital coin to both of you?
yeah.
Because I can just do Control C, Control V and send it. As simple as
Copy the
that.
file.
Right? So
Yeah,
there is no way for us to prevent this double spending apart from, and which is exactly what this paper tries to address. That hey, how do we solve this particular problem of double spending? Okay, so here the few key things that come out of this is the problem of double spending it solves. That's a very key highlight, and how it solves it. That's a very beautiful layered approach that this paper takes by introducing one problem and then solves and introduces another problem and then it solves that. Right.
yeah,
Okay. And to add to that, from the abstract itself, it says that digital signatures provide part of the solution. Now, what digital signatures are? Digital signature is something that tells that because it's a normal public key, basically it boils down to to basically the domain of cryptography, not cryptocurrency, cryptography. The like back in the days when crypto stood for cryptography and not cryptocurrency, from that time.
Correct.
So
Yeah.
cryptography, where digital signature is a way for someone to judge if the information is coming from a genuine source.
Hmm.
So I'll have my own private key and my own public key. My private key would be only with me, and I'll have a public key that can be distributed to the world. Now, what digital signature is? Digital signature, the idea of signature is pretty simple. I'll sign my document with my private key. That can be verified by public key. So this way, if anyone wants to know that if really Arpit is the one who made that particular transaction or it owns that document or anything around that, they can simply
Yeah.
verify. Public key cannot be used to create digital signature. Only private key can be used to do that. So digital signature provides part of this solution because this is where what they are doing is you can know that hey, Arpit really sent money to Kevin. But this does not
Hmm.
prevent double spending because now Arpit can sign the same old copy of the coin and tell ki Arpit also send this money to someone else, let's say ABC.
Yeah.
This is where the
Yeah.
problem of double spending is. Digital signature ensures, or rather, it solves the problem of the thing that hey, someone owns something or someone is saying something which is true, like Arpit only did this, but no one can stop us, like no one can stop me from double spending an electronic cash. Understand? There is no bank involved. Right. Okay.
Yeah.
And then that is where a lot of things would come in when we go through the paper around longest chain,
Yeah.
CPU power, and all. And the core idea it is about that it is this paper proposes a way for us to tell if it is correct or not using a pure P2P network. So there will not be any central entity in the network. No banks, no central database, nothing. It would all be a bunch of computers in the network.
Yeah.
Somehow verifying or somehow knowing that, hey, this is the valid transaction, everything else is junk. Right? That's the beauty
Hmm.
of the implementation.
Yeah.
Okay.
Absolutely.
Anything you're trying to add?
So,
Hmm.
yeah, I think as you mentioned, like this is like a completely P2P
Hmm.
implementation or the solution that is provided mainly to decentralize the control of the power, right?
Hmm.
Like currently banks have this central power,
Hmm.
and we trust the banks to, uh, perform all the transactions in a non-fraudulent manner. But still, there are a lot of scams happening, a lot of problems around that. And then with banks, they have to like spend a lot of resources on that, so
Hmm.
they also have transaction fees. It's also subject to inflation and all those problems.
Hmm.
So creating this P2P network where there is no central authority,
Hmm.
there's no hierarchy among the entities. I think that's the beauty of it, right?
Yeah.
And I think that this P2P model is also implemented elsewhere. Like BitTorrent is one of the most famous ones out there. And I think early internet was also like that, like P2P. And now it has hierarchy, but yeah, previously it was like all the nodes were the same, working together in a way that there's no hierarchy. But yeah, so double spending problem is can be solved, and we will see how it is. I want to emphasize on one thing here. How is it different from other types of digital money? Because we also have, digital coins. Let's say we have Amazon having their own coins. That is also a form of digital money. But I think it's different because Amazon has the control over that, and it's not decentralized, right?
Yes.
Do you want to
So
add something there?
they can literally change the value in their database and your money is gone. Same thing with
Yeah,
bank. Bank can just change your account
yeah,
balance to zero. Your entire saving is gone because you don't have any trace.
yeah,
They own that data. So which is where
yeah.
here you read a line in the introduction which says that a completely non-reversible transactions are not really possible.
Hmm.
Completely non-reversible transactions, which means let's say if Arpit gave money to Keval, if it was a bank, bank can just add another entry in their database. no one can stop them from doing it. Right? So the transaction that we do should be non-reversible. So it should take enormous
Yeah.
amount of effort to make changes to that. So you sending me the money should be more about a new transaction.
Yeah.
You just cannot out of the blue change something. Right?
Yeah.
That is where this is such a beautiful problem to solve.
Yeah. Makes sense. And we'll see how why
Yeah.
it is difficult to change something, right?
Yep. So
Yeah.
what this paper also proposes around basically privacy, that for us, like for example, if Arpit wants to send money to Cavalier, because there is a central authorities involved, like my bank and his basically my bank and your bank, we have to share excessive amount of information, like they would
Yeah.
know our basically social security number, Aadhaar number, address and whatnot. Like why should
Yeah.
we even care? In physical world, you go to the shopkeeper, you don't tell your Aadhaar number, or you don't tell your social security number to that person. You give the money and you take what you want, right? It's pure transactional. But with bank, you have shared a lot of details because they have to build trust with you that you are genuinely a good person and there is nothing
Yeah.
fraudulent that you are doing, right?
Yeah.
This is what another thing that is this trying to solve. Like why should we be sharing excessive information with central authorities?
Yeah.
Okay.
That makes sense.
Hmm. Okay, so the idea here is around everything boils down to cryptography over here. So how do we ensure that a transaction becomes first of all, a transaction is genuine and a transaction is irreversible? That is where we make it exhaustively, literally, it makes it exhaustively difficult for you to add a fraudulent transaction in the ledger. And that's
Yeah.
what the core idea behind the system is. Okay, so we'll start with the second section of it, which is transactions. So which is what the highlight of this is. So when I'm sending money, let's say I'm sending money to you, Cavalier, and if I'm sending money to you, there has to be a place where this is noted. Typically with banks, what we do is when I send money to you, there is an entry in my bank statement. Similarly, there is entry
Yeah.
in your bank statement that hey, you received money from me. So there has to be something like that. That is the first step,
Hmm.
right? And here you
Yeah.
see how beautifully a promise statement is defined for Bitcoin, and then how it addresses. The first thing it addresses is how do we maintain a ledger? How do we define the chronology of the items, right? Or rather, basically
Yeah.
chronology of the transactions, right? So which
Yeah.
is where transactions come in. And what it says that we define an electronic coin as a chain of digital signatures. So again, digital signature, I can sign something, like a person can sign something only with his private key. Other people can just verify the correctness of it. They cannot
Yeah.
make it fraudulent because, and now you say, hey, but I can just fake it, right? Isn't it difficult? That's where the concept of cryptography comes in. The digital signatures are gigantic, right? Sorry, the private keys are gigantic. It would take you literally hundreds and thousands of years to guess a private key of a particular person. So, which is where it
Yeah.
is computationally infeasible to do so, which is what the entire
Yeah.
domain of cryptography lives by. That it should be computationally
Yeah.
infeasible to do something or to basically reverse engineer a system. So, this is what it
Yeah.
is doing, that we define an electronic coin as a chain of digital signatures. Each owner transfers coin to the next by digitally signing the hash of the previous transaction and the public key of the next owner and adding these to an end of the coin. So this is where what you would also do when you are doing it physically. So there is a very nice real world to there is a very nice correlation between what is happening with Bitcoin and what happens in the real world. So what it
Hmm.
says is that each owner transfers the coin to the next by digitally signing the hash of the previous transaction. So it takes a hash of the previous transaction, whatever is there in the ledger. The last thing that is like I did some transfer early, I take that. Now the ownership was with someone. Now I take that piece of information, then I take the hash of that and then I digitally sign. So then I'm adding you because I'm transferring the coin that I had or the information that I had to you. So I'll use, because I don't have your private key, I have your public key. So I'll use your public
Yeah.
key that hey, I Arpit am transferring this thing, something to Keval, right? Now, what all I have is your public key. I have my private key and public key. I have my private key to sign it. So it should be me who is transferring the ownership to you. So I should be the one who should be creating that entry, which is what this is talking about. So this
Yeah.
nicely creates a chain where each transaction, let's say, oh, this is owner one, some transaction it took. Like, let me take the second one. So let's say I'm transferring this to owner one, transfers it to owner two, and owner two transfers it to owner three. So when owner one takes,
Hmm.
it takes the hash of the previous transaction, and then it uses, and then it creates a signature using his or her, like owner one's, it uses basically owner one's private key, and then it assigns it, like it puts in owner two's public key, that I, like it's
Yeah.
like saying that, hey, I, Arpit Bhayani, am transferring this thing to Cavalier. Right? All I have
Hmm.
is your public key. I have my private key. I have previous transaction. So I know where I'm fitting in into the scheme of things. That ownership was
Yeah.
here, which was with me. I'm transferring this
Hmm.
ownership to you. And this forms
Yeah.
the chain,
The
right? And
chain.
which is where the term
Yeah.
blockchain comes in. Each of this item is called as a block, and this is what the term blockchain has come from.
Yeah.
Okay.
Yeah. So
Hmm.
just to add a little summary
Hmm.
there, Joe, so we don't get lost. So we talked about transactions. So transaction is, similar to what we do in the real world,
Hmm.
as in real world, as in the current way of transferring money. So I transfer some money to you, and that is a transaction. So the money is debited from my account and credited to your account, and that is a transaction. So similarly here, we are, transferring coins, or let's say Bitcoin, to from one account to another, and just to make it traceable and not modifiable. We want to create this chain, like who is doing what with this coin and what the chain looks like. And this is the process. We use hashing, and we use public
Hmm.
keys of the person we are transferring to, and we create this
Hmm.
chain, and this is called a blockchain,
Yeah.
right?
Yeah.
Okay,
So
perfect.
this is where what other people can do is, because other people have, let's say, if let's say Arpit transferred something to Cavalier, other people can validate it because they would have our public keys
Hmm.
to validate the authenticity
Yeah.
of the system. Right? Now here,
Yeah.
why it is important to take the history, like why it is important to take the your transactions hash and then create a new one, because with cryptography, if you change even a bit of it, it should become invalid.
Hmm.
So it, like, because you're
Yeah.
computing the hash, even if a bit changes of it, if let's say someone tries to meddle with that, your entire hash, what you're doing, becomes like it becomes
It's
totally
change.
different. Right?
Yeah.
This ensures that if someone just tries to meddle in between something, your entire chain up until that point gets invalidated, because it would
Hmm.
have to redo a lot of stuff to just alter
Yeah.
that.
Yeah. That's the beauty of
That's the beauty
hash.
of hash. Okay. Then what it says is, introduce a central authority or minto that checks every transaction for double spending. This is what we typically do, but this is what they say we don't want to do. Like basically, when
Yeah.
we do this transaction, who ensures the who ensures the correctness of it? That is where a common solution is to
Yes.
add a central authority like bank, which is what bank play a part over here. But we don't want to do what we don't want to do that. The problem with this solution is the fate that the entire money system depends on the company running the mint, the bank,
Hmm.
right? They can do
Yeah.
whatever they want to do with that. But we trust the bank that they won't do any fraudulent
Yeah.
stuff, right? Previous
Yeah.
owner did not sign any earlier, like, how do we know? So this is where the paper introduces another problem and the way we would want to solve that. That how do we know that person is not double spending? Because here, till now, we have not solved double spending problem. If this
Yeah.
block, I can just take this block and transfer it to UKV and transfer it to some user ABC. This is still not a solution of the problem. So we are still defining the
Yeah.
problem that, hey, we have still not solved double spending problem. We have to find a way to solve the double spending problem such that the
Yeah.
participants agree on a single history, that the ownership
Hmm.
of something was transferred from Arpit to KV and from KV to ABC, from ABC to PQR. There should be a way to identify the single lineage of transfer. Okay.
Perfect.
And more importantly, this is the most important part over here. The payee needs the proof that at that time of the transaction, the majority of the nodes agreed that it was first to receive. In simple words, that if I transferred the ownership to KV, KV needs to know that Arpit definitely did not double spend. And
Yes.
not just me who is just transferring it and saying, and I did not transfer. You also have to be extremely
Yeah.
sure that Arpit is not double spent. It should be a
Yeah.
bi-directional affair. Right? Okay.
Yeah. Yeah.
So which is where what it introduces, we come to the third section of it, which is where it introduces timestamp server. Now what timestamp server says? It says that a timestamp server works by taking a hash of a block of items to be timestamped and widely publishing the hash. Okay. Too dense of an information. So what Bitcoin does, Bitcoin is basically essentially a network of nodes. Right? Now, whenever you do a transaction, that transaction, let's say let's say Arpit wants to transfer money to Kevin. This transaction goes to a particular node. That particular node gets that particular transaction. It would try to add that transaction to a block. Now, this block contains multiple such transactions. So think of it like an in-memory buffer, in which whatever
Hmm.
transaction you are getting, you are buffering it in memory, right? Which is what this block is all about. And now from this
Yeah.
block, where you put in all the transactions, which is where you have to create multiple such blocks. And that's why Bitcoin is just a massive blockchain of such transaction records. Each block contains multiple such transactions. That let's say Arpit transferred to Cavalier, some other person transferred to some other person, something else. It should not be related to one transaction or that one ownership. It can be
Hmm.
anything.
Yeah.
And all of this is put into a particular block. Right? And this, when you say block is minted, this is what this block minting is all about. The people or the nodes
Yeah.
would be creating these blocks. And how would they get this transaction? Because the timestamp, they are widely publishing the hash. The transaction hash, they are continuously being published across the network. So they're continuously getting
Yeah.
these hashes of all the transactions that are happening, and they're trying to place that into their corresponding blocks, and they're all trying to mint their corresponding blocks. One of them would win, and that's what that person would be rewarded with the Bitcoin. Okay.
Yeah.
Hmm.
And that adds a lot of
Yeah.
transparency around what is happening in the network. So there is no one node or a group of nodes that are acting fraudulent in a fraudulent manner, but it's all transparent. Everyone knows what is happening around the
Hmm.
network. Unlike we don't know at this point what is happening inside a
Hmm.
bank. If one employee decides to change the records, he
Yeah.
can do that. But here we have full transparency. That is another beauty of
Yep.
this.
And here, each timestamp includes the previous timestamp in its hash, forming a chain. So that same hashing
Yeah.
concept that we saw earlier, that same thing, just in a little more abstract way, where instead of just putting in one transaction, we are just adding that there are multiple transactions like this, and the chain is formed. Okay.
Hmm.
Then the fourth. Now this is where things become interesting. This is where the proof of work comes in. Now we added
Yeah.
something to the chain. We know blocks are there, but how, like, now anyone can add now. Anyone can add chains to the blocks. How do we make it harder for people to do it? Because why do we want
Yeah.
to make it harder? If we don't make it harder, everyone would do it. Everyone start adding blocks. Everyone start creating their own set of blockchains with some their fraudulent transactions, because this is a P2P network. This is zero trust network. Now you cannot literally trust anyone. Anyone, if you don't make it hard enough, it just, you can like create as many blocks as you can, saying that hey, now Arpit owns Taj Mahal as well. Right? You can just create
Hmm.
entries like this. You don't want that to happen. That should be
Yeah.
extremely difficult to do so. Now that is where proof of
Yeah.
work comes in. So proof of work
Yeah.
involves scanning for a value that when hashed, such as with chart 56, the hash begins with a number of 0 bits. Now again, really tense. So now what it says is, earlier in the block, what we added all the transactions that we wanted. Right? Now here, we take the previous hash, we have a lot of transactions placed in the block. Now in this block, we have to add one more thing. This thing is a nonce. It's just a one-time value, right? It's basically kind of an OTP, one-time password. It's that
Hmm.
kind of singular value that does not have much significance except the fact that it should meet a certain criteria. So what is a nonce?
Yeah.
In my transaction block, what I'm putting in multiple transactions, I should be adding a value nonce such that when I compute the hash of this block, it starts with a specific set of zeros. Now, why zeros? Because like a block starting with a large number of zeros, it's very hard. Now imagine writing a function like you have some data. Let's say assume you have some data, some text. You pass it through SHA-256 value. Or sorry, SHA-256 hash function. When you pass through that, it
Yeah.
gave you a hash value. What are the chances that that particular hash value starts with, let's say, 5 zeros or 6 zeros or 7 zeros? Very, very, very
Yeah.
rare. So this is where you or your Bitcoin node has to add this value, literally iterate through this number 1 to it reaches till integer 32, it reaches till 4 billion. From 0 to 4 billion, it has to continuously try every single number until the output hash of this particular block, like this particular block, when I hash, the SHA-256 hash of it should contain some n number of zeros in the beginning. Now, this
Yeah.
is the grunt work that the node has to do so that that block gets minted, which means that once it finds that nonce such that the block starts with a fixed number of zeros, that is when we say that, hey, I found this value, because for other nodes to find it, it would be extremely difficult. There is no way for them to do it. And like the best way is to start from zero and reach till 4 billion. There is no random work that you can do. But to literally start from zero,
Yeah.
reach till that point so that you find that magic nonce such that the output SHA starts with a zero. So if you go through any website that shows you the current Bitcoin node, and because it's a P2P, everyone has the data, right? Everyone knows from who transferred how many Bitcoins to who. You can see all the
Yeah.
blocks starting with a fixed number of zeros, right? So
Yeah.
that's the magic of nonce. And this is the proof of work, because now, given that my pure P2P network has zero trust, anyone can meddle with a lot of things. We have to make it tougher and tougher and tougher for people to do that. That is where we added this proof of work. Now, the beauty of this algorithm, every single block starts with a fixed number of zeros. Now, if you change something in a block, now that block's hash will not start from zero, so no one would be accepting that block. People would know that this is fraudulent,
Yeah.
right? Other part would
Yeah.
be that if you change a hash in one thing, because the output of this hash is connected with the next node, and then with the next node, and then with the next node, every single node in the chain is getting affected by it. So now you have to do the
Yeah.
grunt work for not just your node, but all the nodes up until that stage. I have to do so much of work to just spoof my fraudulent transaction. And now this work is not small.
Yeah.
You have to literally apply CPU to find that nonce for every single block, such that that corresponding block starts with n number of zeros. And
Yes.
that's the beauty of this,
That's the
that
beauty.
it would making
Yeah.
incredibly difficult for people to add fraudulent transaction into it.
Yeah. That's really beautiful because we are slowly moving away from the trust based model to a more proof of work based model, because we don't trust anyone, we don't trust any machine
Hmm.
on the node, and they have to prove that they have done the work. And the way they do it is by putting those CPU cycles and finding that number or the nonce that can be added, such that
Yeah,
n number of zeros can be found at the beginning of the hash. And then it's not easy to change, as you said, because changing one bit changes the entire
yeah,
hash. And unless you are really lucky and that you find the same number of zeros again, which is almost impossible, you cannot change the block or the chain of blocks, and no one will accept
correct.
your chain as the true chain in the network. So that makes it even harder, because you have to put
Yeah,
in that work. You cannot just fake it, you cannot just just
yeah,
mimic the work. You have to do it,
yes,
because this is such a boring thing to do, right? For just to make it a little more simpler for our viewers. So the nodes are simple machines on the network that are just connected to each other. And for example, I have to run this process, or I have to prove that I'm doing this work. I just have to run like a loop from one to the number, and then find out that number which ends up getting in this hash, and that requires so much CPU power. So unless I have unlimited amount of money, unlimited control over the entire, let's say, AWS servers, that I can spin up, let's say, 10,000 machines or even more. It's really hard to, do it simply. Maybe it is possible for someone who has extreme power on resources, but it's simply not possible the way it
Yeah.
is designed. So yeah, it
Yeah.
is really beautiful.
And let's say if I already have a massive blockchain where a lot of transactions are there, let's say I want to add my fraudulent transaction in between, right? So let's say I just want to add, let's say I want to add this line, let's say basically KV owns Arpit $1 million because this is P2P. I should be able to do that. If I change that,
Yeah.
because output of this hash is connected or is used into the block after that and the block after that, I have to redo the work
Yes.
for the entire chain after that, right? So from the point where I'm
Yeah.
changing to the entire chain, now imagine if you would want to, the more you would want to go back in the chain, the harder it would become for you because you have to compute nonce for every single block such that the block starts with a fixed number of zeros, and then other nodes would also need to accept that. So a lot of computation would go waste because it would be slowed, because while you are
Yeah.
computing it, other blocks are getting minted. And that's even more pathetic because now you just found out, somehow you just found out 10 nodes. For 10 blocks you found out. But then up till then, three more blocks are minted. Now you have to do for three more blocks. And then
Yeah.
more blocks are minted. So those are the things that makes it really interesting. Okay.
Yeah.
Now here you say, okay, that's still okay. I should be able to pull that off if I have a lot of machines. Now here, because what these guys do is, this is like voting. So here what we are basically doing is, because of these hashes that we added, because of this nonce, the idea of majority, instead of it become one IP one vote, it has become one CPU one vote. That's the idea over here. It's
Yeah.
easy to gather
Yeah.
IPs because more machines you buy, even smaller ones, you can get multiple IPs. So that's where what this paper beautifully talks about is, instead of relying on IP based voting, it is relying on CPU based voting because CPUs are expensive. So for you to do that computation,
Yeah.
you should not be just purchasing large number of small instances. You need gigantic instances to do it. So this is what it
Yeah.
is essentially trying to do over here. Okay. Then what it says is the longest chain which has the greatest proof of work, effort invested in it. So the longest chain. So now the nodes, what they would do, nodes would treat the longest. So every node in the network would get the entire ledger because it's P2P, right? Every node gets the entire ledger. And now let's say I get the entire blockchain. Now I get multiple such blockchains from there, and I have my own copy of the blockchain.
Yeah.
Now, if I'm minting,
Yeah.
if I get some other block, now to which chain should I add it? Because I don't know which one is true.
Hmm.
So that is what it says is, the longest chain in the network, or like the longest chain that you have, is the correct one because it required a lot of proof of work to reach till that stage. And it would be harder for
Yeah.
anyone to spoof that. So given that, that is where a simple logic where you are giving weightage to the longest network or the longest chain in the network to be the truest one. Okay, if a majority of CPU power is controlled by honest node, now this is where you come to honesty, where it says that if majority of CPU power is controlled by honest nodes, the honest chain will grow fastest and it would outpace the
Yeah.
competing chains. So if you would want to even compete, if you want to even add fraudulent chains in the network, you would need enough power to do that, because if there are
Hmm.
more than 50% of the nodes which are honest, they would be minting authentic transactions. They would be much more likely to mint more blocks and keep on adding to this honest chain that you have versus someone
Yeah.
who is trying to do fraudulent. So if you are the only fraudulent node in the network, you're not able to create large chain
No.
out of that. You don't have enough
Yeah.
CPU. Now that is where you think it, but what if I did that? Now for you to do that, you need more than 50% of the power, because that's when you would be faster in minting fraudulent transactions than the honest
Yeah.
one. So that's when you would do that. Now you're thinking, if I already have 51% of compute power, why don't I use it for normal thing and I mint Bitcoin? Why do I want to add fraudulent transactions into that? So
Why not just become a good guy?
yeah, when you have enough, just basically become the good guy. which is where it is saying that
Yeah.
the probability of a slower attacker catching up diminishes exponentially as the subsequent blocks are added, because the pace at which the blocks are added is much larger than a fraudulent node who is trying to mint. Because imagine how much of CPU you have. For you to add that, it would take you so much of time to compute the node. So it diminishes exponentially because the honest
Yeah.
nodes are minting blocks back to back and adding it to the chain that you are not able to cope up. And
Mm.
this is the beauty of it, that this is what the 51% attack that you all might have heard of is all about. So in that series,
Yeah.
Silicon Valley, they did this 51% attack in the pre-finale episode. This is what that 51% this is exactly what 51% attack is all about. So if you are in a P2P network and you own more than 51%, if you own more than 50% of the computing power or the nodes, then you own the network essentially. In normal world, you
Yeah.
think that, hey, if I just have more nodes, it's good. But here, because it is proof of work, it is CPU based. Because it is CPU based, it would be much more expensive for you to gather it, which is why it is much, 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 much harder. That's why they move from one IP, one node to one CPU, one node.
Yeah.
Yeah.
That makes a lot of sense. And and also the probability of the attack is, governed, as it says, by the more or the faster the blocks are
Mhm.
added to the chain, the more difficult it is for the attacker to actually uh, succeed in the attack, because then he has to process more number of blocks and create or generate all these hash for the new chain that he has got. And it adds a lot more complexity and a lot more work to be done.
Just to add to
So
that,
yeah,
what
that
kind of
makes it really
fraudulent
hard.
transaction would someone add? Like for example, that person added a fraudulent transaction. Let's say KV owns Arpit $1 million. That one entry. To add that one entry, that user would have to change that entire chain and then add more blocks to it so that it owns
Yeah.
the largest chain. Now, just to add that one or few
Yeah.
more, like add more such fraudulent entries into that, for you to own that, you have to do so much
Mm.
of work. It's not worthy. Right? Just become a good guy and be part of it.
And that's yeah, absolutely. And that works
Yeah,
requires a lot of money.
insane amount.
So so your probably cloud
Yeah.
bills will be higher than the gain you're
Yes.
getting from the fraud. So it's
Yeah.
better to be the good guy.
Okay. Then coming to the fifth part, which
Awesome.
is network. So what network says is new transactions are broadcasted to all nodes, which is what we talk about. That it's a P2P network. Whenever I do a transaction, let's say
Mm.
Arpit transacted something with KV, this would be broadcasted in the network. Every node is continuously listening for incoming transactions, not blocks. I'm talking about transactions. So any transaction happening on the node, it's
Transactions.
coming to all the nodes in it. Now, obviously, you cannot
Mm.
guarantee delivery of the transactions. Now, imagine you would not be sending it to every single node in the network. You just want to ensure that your transaction reaches
Yeah.
to more than 50% of the nodes. That's all you'd want to ensure because it's P2P. Each
Yeah.
node collects new transactions into a block. So that's what we talk about. In a block, you have multiple such transactions. They're collected
Mm.
in a block. Each node works on finding the difficult proof of work for its block. This is what we talk about. That when they added all these transactions, they have to compute the nonce for that. Now then they add some transactions to that, then they start computing the nonce. If new transactions get added, they would be placed in a in-memory buffer, and then they would be trying to compute the nonce of whatever they have in the block. And all the nodes are doing it. It's not just one node.
Yeah.
Every single node is doing that same thing. Now imagine
Yeah.
some nodes might receive transaction A, B, and C. Some nodes would receive A, B, and D. Some nodes would receive E, F, G, right? But they are all trying to mint that same thing and somehow come to a conclusion that this is the order in which the transaction happened, right?
Order.
So,
Yeah.
which is where this is
Yeah.
what the beauty and the beast of P2P networks is, that you cannot tell the
Yeah.
order in which. So that's why you have to rely on timestamp, which is where the timestamp server comes into the play. You have to decide on, hey, this is the like basically this is the order of the transaction, and timestamp server is basically just chaining it with hashes. That essentially becomes the fact that this is how my transactions are ordered, because one of the blocks would be able to find the nonce, would be announced, everyone would get it and would be adding it to that corresponding blockchain, which would mark the chronology of the transactions.
Yeah. Yeah. And anyone who finds it after the fact, then that transaction would be
They have
invalidated
to
because that
redo
is already
the
done.
entire work.
And
Now let's say transaction A, B,
yeah,
and C are accepted, while someone who was trying to find, because see, there would be two nodes. Let's say I have transactions A, B, C, and D total, right? But no one knows that there are four transactions A, B, C, and
yeah,
D. Node one did A, B, and C,
yeah,
created a block and trying to find the nonce. Someone tried with A, B, and D. One of them would find the nonce for
mm,
that particular array because they would be having
mm,
that same blockchain up until, let's say, block zero, right? From block zero's hash they would be
yeah,
conducting. Only one of them would be succeeding, like the first. The one who succeeds,
yeah,
the block would be added over here. That node would be, other information would be broadcasted.
mm,
Now, let's say A, B, and C node was succeeded, like with that block was minted. Then the person who was doing with A, B, and D would get this information that array, someone else won the lottery. Then that person would be, or that node would be dropping AB because ABC was already done. Transaction ABC are part
yeah,
of the blockchain. So it would
already done.
drop that. It would add another transaction
Yeah,
into the block. So D, then let's say EFG, and then trying to compute the nonce. Now, so much of repetitive work is doing, which is
yeah,
what this contention is all about. Everyone's trying to mint the block,
yeah,
right?
yeah,
Okay. Then when a node finds a proof of work, it broadcasts the block to all the nodes. Nodes accept the block only if all transactions in it are valid and not already spent. Now, how do we do that? Digital signature. You will not just accept anything.
mm,
And if you get a particular block that, hey, if a node announces that, hey, I have this block minted, I found a nonce, that block would be announced to all the node. Now, all the node upon receiving a block, up until now, we are receiving transactions. Now, if they receive a block that this block is new minted, every node would check because no one
mm,
trusts anyone, right? So they would check if this node is actually all the transactions, hashes match, entire blockchain matches or not, right? That entire hash, it's just
yeah,
about digital signature verification. It's not an expensive process. You just have to validate the digital signature throughout
yeah,
the chain and you're done with that. Right. And once they accept it into their blockchain, that becomes a new node. If they were already processing something, node expresses their acceptance of the block by working on creating the next block in the chain using the hash of the accepted block and the previous hash. So as soon as I know that the block that I got was valid, now whatever effort I put in are all waste. Let me try to mint a new block
yeah.
with this block as my previous block
New block.
and
Yeah,
see if I'm lucky enough to find the nodes. Okay. Hmm.
yeah. So whatever work you have so done so far is kind of wasted, and you have
Yeah.
to,
Yeah.
restart.
That's the
Yeah,
that's the best part of it. Like you have to do so much of work, and which is why it makes sense that if you already own 51% of the compute power, do it for the right thing. You'll earn more Bitcoin than if you're trying to be
yeah,
fraudulent in the network.
exactly. It has made so frustrating for the fraudulent folks who want to do something
Yeah,
that they will just give up. Okay,
exactly.
let's be good guys, and
Exactly.
forget about
Yeah.
fraud.
So nodes always consider the longest chain to be the correct one because the greatest proof of work, and will be keep working on that, extending it. If two
Yeah,
nodes broadcast different versions of the next block simultaneously, some nodes may receive one or the other first. The work on the first one they received,
mm,
but they save the other branch in case it becomes larger. So I received two blocks
yeah,
sent me, or rather, sorry, two nodes sent me two different blocks that they say, we minted the block. But then what is happening is they're
yeah,
just keeping them handy because because now you have two divergence, and obviously only one of them would succeed in going to the next one. The one that
yeah,
becomes the longer would be considered as the original one. Everything else is dropped off.
yeah,
Okay, the
yeah,
tie is broken when the next proof of work is found on one branch becomes larger. The nodes that are working on the other branch will switch to the longer one. So they keep track of everything that they received. Only one of them wins, the one which is the longest one. In case there is a tie, they would wait key who becomes longer, and then they accept and then they move forward with that.
yeah.
Hmm.
While I was reading
Hmm.
this, I got a question in mind that, if this race condition happens, that okay, you
Hmm.
now have two branches, and then you still keep the both the branches, and then you keep processing to eventually know which one is the longer one. But then you again end up in the same race condition, and again end up in the same race condition. So will that be a problem? So it looks like they wait until like six times for
Hmm.
this race condition to happen, and then they say that six time is already a lot to for this race condition to happen, and at that time you will end up having a longer chain, and the other
Yeah,
branch would
yeah,
be just discarded as invalid.
yeah.
So yeah, that makes a lot of sense.
Okay. Now this is where the edge cases we talk about that it's possible that the new transactions broadcast do not necessarily need to reach all the nodes. As long as they reach many nodes, basic
Yeah,
majority of the nodes, they will get into a block before long, right? If a node does not receive a block, it will
yeah.
request, another edge case where it is possible that a block is minted, but a node did not receive it. What would happen
Hmm.
if a block receives some other node, but not a node before that, or not a block before that? It would know that, array, because the
Hmm.
previous hash of this is something else. I don't have this block. So it would ask the network to send the
Yeah,
block, right? So in case a block is missing, you get
yeah,
that. In case a transaction is missing, if many nodes have it, if let's say if some transaction is missing, then you are just unlucky. So you typically have a lot of gossip happening that is continuously sharing the information
yeah,
about a transaction in the network, and very rare for you to not receive
yeah,
the transaction. Okay,
yeah,
the sixth one, which is where it talks about incentive. That why would someone do that? Why would someone put in money? And this is how the beauty is. Like we started with ledgers, then we added proof of work, then we talked about network, right? This is like we are solving one problem and then we're discovering another. Now you talked about, hey, we need multiple nodes, or we need a majority of the nodes to be good to do this. But why would someone do that? This is where the sixth part comes in about incentive. It's this paper itself is a blockchain where it beautifully links one to another and then discuss another and then to another, which is what I liked about this paper. So
yeah,
incentive, why would someone do that?
yeah,
So a steady addition of constant amount of new coins is analogous to gold miners expending resources to add gold in circulation. In our case, it is CPU time and electricity that is expended. So now for someone to think about that, hey, I want to purchase servers. To do that, they have to be given something in return, which is what is we call now Bitcoin. So when someone is putting in or someone is minting the block, they would get money in return. Now, sorry, so they would get Bitcoin in return, right? That because they put in so much of effort,
Hmm.
they in return they would be getting this Bitcoin. Now, what are they putting into use? They are putting it into
yeah,
use is CPU and electricity. Similar to this, the real world analogy is gold miners. Gold miners use their brute force to mine gold, right? The one who gets the gold, it's literally creating gold out of
yeah,
nothing. You didn't have gold. You literally mined the gold.
yeah,
So your effort that you're putting in, you're rewarded by the gold that you have. And this gold has some intrinsic value,
yeah,
right? Similarly, Bitcoin also has some intrinsic value. Right? Okay. If the output
yeah.
of and basically this is the first one where you get Bitcoin, but there are limited number of Bitcoins. Like we all know that there is some number is there that only these many Bitcoins would be there. After that, you would not have Bitcoin. So that is another incentive is
I
it's
think
around
it's
21 million.
21
You
million.
would not have more than that. The incentive can also
Yeah.
be funded with transaction fees. So which is where what it adds to the
Hmm.
fact that if let's say I am transferring 3 Bitcoins to UK, then they might say 10% is the transaction fee. So if I would want to transfer 3 Bitcoins to you, I have to actually transfer 3.03. So that 10%, sorry, 3.3. So that
Hmm.
10% goes to you. Sorry, 10% goes to the one who is
Yeah.
or like the one who mints the block. That
Mine.
person or that node or that person
Yeah.
would get that particular money. That's a transaction fee. That it's my effort who like I have
Hmm.
minted so many things. So it's the all the transactions. Now here, the one who mints the block, that block has a lot of transactions, right? One block has multiple transactions. Each transaction could have a
Hmm.
transaction fee. The summation of all of those transaction fee would go into your account. That you have this much of transaction fee, and now you are earning money from that. That's the idea from it.
Yeah.
Now, this incentive would help and
Yeah.
or would basically help encourage the nodes to stay honest. If a greedy attacker is able to assemble more CPU power than the honest node, he would have chose between using it to defraud people by stealing back his payment or use it to generate new coins. Generating new coins is much better than doing this fraudulent transactions there. Yeah. He ought to
Fraud.
find it
Yeah.
more profitable to play by the rules. Like this is such a central idea to this. In a P2P network, zero trust model. You cannot
Hmm.
trust anyone. So you have to promote honesty. And this is such a beautiful way to do that. That it should be
Yeah.
more profitable to play by the rules versus against that.
Absolutely. So this is really beautiful because let's say in banks, so you have employees, but they have this fear of audit that happens, let's say every 6 months. So
Yeah,
if I do fraud, there will be audit, right? But still there is some possibility that you can also
yeah,
give money to the auditor and find some ways around it. But here it's open. It says do it if you want to, try it, give it a try. If you can, just make it fraud, but
yeah.
it's we are saying it's impossible. So we don't make rules or something, we just say there are no rules, just try it and
Yeah.
fail, and you will figure it out that fraud is is
Exactly.
not the way to go.
Yeah.
So it's really beautiful.
Which is why I love exploring P2P, because P2P by default has to be zero trust model. And there are
Mm,
like, it's such a
yeah,
beautiful thing that it's like teaching your child to be honest. It should be more profitable for the child to be honest. Like, if you know, if basically cheating is easy, you would be cheating in examination to get marks. But if honesty is promoted, which is where you say that if we find you cheating, then you would be failed in the examination. That fear of failure is the one that is transferring. So it is more beneficial for them to be honest. So if a teacher is really strict and he or she says that, hey, if I find you cheating, your
yeah,
entire year is gone. There is so much of de-incentivization for you because of, like, for that, it's fear. It is profitable for you to stay honest. That I'll just get passing mark, but I won't cheat, because the loss is much
yeah,
higher. Similar to over here, you'd be losing money into putting the CPU power and whatnot if you're trying to be fraudulent. Right? Yeah. Okay.
yeah, absolutely.
Now, this was the network part that we talk about. The incentive part was the most technical of it. Now, these are optimizers. Now, from here, the performance optimization starts. Reclaiming the disk space. This is where we talk about that in every block, you have large number of transactions. It is typically 1,000, 2,000, 3,000 in that range, but it could vary. So you have, let's say, 3,000 transactions in one place. In each transaction, you have this person send this person this particular thing,
Mm,
right? So this block becomes huge. Imagine for each block size, it would become pretty huge for your nodes to keep that. So you would require a lot of disk space to keep those nodes on your
yeah,
disk. So can you do something about that? I don't want to, like, imagine you want to be part of the Bitcoin network, but you have to download the entire blockchain, and that would be huge. It's not literally, like, it's not many terabytes, but you don't want it to be big enough,
yeah,
because downloading that much of data itself would require a lot of
yeah,
network. Why would you want to do
yeah,
that? So that is where, in a Bitcoin network, there are two types of nodes. One is a full node, and second one is a partial node, which just stores the meta information. So which is what it is talking about, claiming the, or basically reclaiming the disk space. So what it says is, instead of you keeping the entire block, just keep the information of the block that matters to you, which is the block header. Now, block header would contain what? For what, basically whatever you need to compute the
yeah,
hash, just to verify the blockchain. The previous hash, nonce, and the root hash. Now, this root hash is what? It's the Merkle tree of, like, it's the hashes of the transactions that you have put it in the
yeah,
block. To put it very simply. Now, instead of just storing the normal hash of the transaction, what we are actually doing is we are creating a Merkle tree out of it. Now, what Merkle tree is? Merkle tree is basically a tree of hashes in which at the leaf node you have the actual transactions. Here you can see at the leaf node you have actual transactions. Each transaction is hashed to some value. Now, if I have, let's say, four transactions, T0, T1, T2, T3, I'll take the first two transactions and create a new hash out of it. It is hash 01, which is the hash of transaction 0 and 1. Hash 2 is for transaction 2 and hash 3 is for transaction
yeah,
3. I combine these two hash to create a new
yeah,
hash. And hash 01 and hash 23 combines to create a new hash. That becomes a root hash.
mm,
Now, if anyone wants to change anything, any transaction in that, this entire Merkle tree would change. That's the beauty of it,
yeah,
because it is hash of hash of hash of hash of hash. So if anything, similar to how you have blockchain, if you change one thing,
subsequent,
the entire chain after that would
yeah,
change. Similarly, in Merkle tree, if you alter hash of one node, it changes everything till the root. Your actual root hash would be changed. So you'd know that someone tampered with that.
mm,
This is also used by Git for source version control to identify, your basically commit tree, or to identify what change on your disk, what change in your in your basically current working
Yeah.
directory. It uses that to
Yeah, yeah.
identify that.
This is also used
So,
in some of the
hmm,
databases like DynamoDB. They use it to check like two hosts or two nodes. What is the status in terms of synchronization of data? And if the hashes match, they say, okay, this data or these key ranges are already synced, so we don't have to do any replication. So it's
correct.
very interesting. Yeah.
Correct. Yeah. So they use Merkle trees to do that, and which is where now they only need to store the root hash of it. They don't want to like though they
Mm,
don't need to store anything
yeah.
else. So now this means that you don't need to store the actual transaction information, just one hash representing all of
Yeah.
them. If someone tampers, everything gets
Yeah.
changed.
So
Right?
this is
So
just a
this is how
verification
you
step. So
replace
it's
this.
it's you don't
Yes.
need to store like entire thing when you can just store the hash. And this is another
Correct.
like really good optimization. Although it's not huge data, but it still can be huge and it's unnecessary. So why
Yeah.
not optimize?
Yeah. Yeah. And it's pretty huge in terms of 100 to 200 GB. 316 GB is what I heard the
Okay.
last, that is the size of the blockchain at the moment.
Okay.
But it can grow out to be 1 TB, 2 TB
Yeah.
as
Yeah.
well,
Yeah.
because it's the amount of information that we're putting in
Mm,
that. Right?
that's
So
right.
it totally depends on that. So it can grow out to be pretty large if we don't maintain, which is where every node also has a limit. And that's a practical implementation of it. This paper does not enforce
Yeah.
anything. It is not spoon feeding us the
Yeah.
implementation. It's just saying what you can
Yeah.
do. Bitcoin, as we know today, has the actual implementation of it, but it has also covered basically many of the practical aspects of it, but relying on the same principle. Okay, so that is about doing this part where we reclaim the free space from the disk, and then here it like look at how beautiful this paper puts out here about Moore's law. The world runs on Moore's law, and with computer systems typically selling 2 GB of RAM as of 2008, that person foresaw from 2008 to in 2022 that with Moore's law, this would be cheaper, like your disk space would be cheaper,
Yeah.
right? And Moore's law predicting the current growth of 1.2 GB per year, storage should not be a problem, even if block headers must be kept in memory.
Mm,
So that person was so ahead of its time that person thought about
yeah.
it that right now, if I'm putting my blockchain, right now it might not be possible for me to fit it in memory, but you might see systems where I
Mm,
can put my entire blockchain in memory. We have 1 TB RAM, 2 TB RAM as well. We can keep the entire blockchain, full transaction information in RAM. But why should we? We can at least store block headers in RAM.
mm,
And that is what we should be easily be able to achieve throughout the year.
yeah.
Like in the future, we should be able to achieve
Yeah.
that. Okay. Then section 8, it's about simplified payment verification. Now that we have that information, now that we know about we did optimization, PayPal accepted that. Now, how do you verify payment? Because this is where you come towards the practical usage of it. Now, how do you verify the payments? This is where what we do that it is possible to verify the payments without running a full network node. This is what I was talking about. That there would be a lot of nodes in the network whose job is to simply verify if this transaction is valid or not, right? Or verify if the block is correctly placed or not. So to verify that payment, you don't need to run full network node, because what you can do is you can have just use block headers to just verify the correctness of the chain. You don't have to do anything else with that.
Mm,
A user only needs to keep a copy of the block headers of the longest proof of chain, which he can get by querying the network nodes until he is convinced that he has the longest chain. So this way, for anyone to verify, let's say, I just want to verify if the blockchain is correct or not. I can do that without downloading the entire blockchain,
mm,
because I just have to download the block headers and I can simply verify that particular thing. I don't need to recompute the hash of every transaction and do that.
yeah.
I can just do this very quick verification, which is what nodes would also be incentivized to simply verify the correctness of a particular
Yeah.
transaction, or the if the transaction is not fraudulent enough,
Mm,
right? He can't check the transaction by himself, but linking it to a place in the chain, he can see that the network node has accepted it, and the blocks added after it confirm that the network has accepted it. So there would be network in the nodes whose job is to simply verify that particular thing. So you don't need entire thing. You're just storing the hash over here. You can just verify it by traversing the block headers. You don't need to be a full node
yeah.
over here. And like always, the verification is reliable as long as honest nodes control the network, but is more vulnerable if the network is overpowered by an attacker. Because people can say, or the fraudulent nodes can say, no, this transaction is valid even though it is not. Like it's like in a crowd, if you are surrounded by 100 people, in out of 100 people, 51% of people say something
Hmm.
that, let's say, Earth is flat. 49% say no. Eventually, that 49% of people would have to agree with what 51% of people say, otherwise they would kill them.
Yeah.
Right? So, which is what happens here as well. So long as honest nodes rule the network, there would be no problem.
Yeah.
When majority of the people become corrupt, when majority of the nodes become corrupt, that's when the problem starts to creep in. Businesses that receive frequent payments would probably still want to run their nodes for more independent security and quicker verification. So here, what it says is the fact that business like enterprises might not very heavily trust the Bitcoin network.
Hmm.
This is exactly what they are talking about. That for them to ensure the correctness of the blockchain, they would not want to do that. So for them, it should be easy. Like it should be easy for anyone to verify the correctness of the blockchain.
Yeah.
So which is where you can run a separate node whose job is to simply iterate through the block headers and see if it is correct or not. So they would want to. So this is again best part of Satoshi, that person, the group, whoever they are, he is, they thought about this, that enterprise, for them to adopt this, they just cannot rely on the truth of the blockchain.
Yeah.
They just cannot blindfoldedly adopt it, or they just cannot blindfoldedly trust it.
Yeah.
They would want to be very sure on what they are doing, that if it is correct or not.
Yeah.
And then combining and splitting value. This is where the transactions would be there. So about Bitcoins, like how we are doing money transfer and whatnot. So what it says is to allow the value to be split and combined. So here, let's say I want to, like, we can transfer Bitcoins in decimals as well, in very small fractions.
Yeah.
0.0001 BTC. Like how does that happen? Because when we get a Bitcoin, like earlier when a block mints a Bitcoin, let's say that block got like 3 Bitcoin. In physical world, let's say you have $1. You cannot just break $1 into something. You can break it to cents, but you cannot send half a cent to someone. So what if the value of a Bitcoin, when we're trading it, let's say it goes very huge. You cannot trade it. Like you cannot just say, like, this is the bare minimum that I have, sir. Because it is electronic, this is the beauty. Because it is electronic, you should be able to send very fractional amount to someone. So how do you do that? So which is where this part talks about, to allow value to be split and combined. This is the problem statement. How do we do that? Either a single input from a large previous transaction or multiple inputs combining smaller amounts. So either, let's say I want to transfer 3 Bitcoins to you. Then in some other transaction, it would have written that Arpit received 7 Bitcoins. I will use that transaction, either that, or let's say I received 5 transactions, or rather, let's say I received 10 transactions of half Bitcoin. Out of that, I would be picking 3, like, which sums to 3 Bitcoins, and then I would basically send it to you. Right? So the input is what here is talking about. Input is either a single input from previous large transaction or multiple inputs combining smaller amounts.
Yeah.
Now these become the input of my transaction. Now what's the output? Output are 2. One, that I have sent money to you, the amount. Let's say I have 7 Bitcoins came in one transaction. Right? Now someone, let's say ABC sent Arpit 7 Bitcoins. You want 3 Bitcoins from me. Right? So I have one large single input with me, which is 7 Bitcoin. That one transaction. Now from that, I want to transfer to you 3 Bitcoins. Now when I would want to transfer 3 Bitcoins to you, now here what would happen is, from this one single input, I'm sending 3 to you and then sending 4 to myself. So this is like I've spent 7 such that 3 went to you and the change is added back to my wallet. So basically the entry of the transaction would be like that Arpit sent KV 3 Bitcoins and change is added of 4 Bitcoins. So you would like spend 7, sent 3 to KV and received change of 4. This is the exact information that would be stored in the particular transaction, in which would be fitting in a block.
Yeah.
This way, it allows you to send partial, very fractional amounts as well, because it does not limit us to do anything. Like imagine this is not a barter when you have a kg of rice. You want to send some part of it. So you would write, I send 1 kg to you. You took what you wanted and I added back this much. So now the unit that I have is, let's say, 4 kg. I had basically 7 kg of rice. I would say to 3, I would get 4. So I write spent 7, change is 4. Now that becomes part of my wallet, and I gave 3 to you. So it's basically I split the value
Yeah.
into 3 and 4. I kept 4 to myself, writing another entry as I received the change of 4 and
Mm.
giving 3 to you.
Yeah.
So this way, effectively, I have 4, but the entries added such that it that I received a change of 4.
Mm.
So this is how you would be storing it. This would make basically balancing much simpler, because now you
Mm.
are literally breaking your Bitcoin into what you have transferred and what you are left with,
Mm.
right? So that becomes a wholesome thing for
Yeah.
you. Okay, now this is mostly the final part where we
Yeah.
talk about privacy. In privacy, here it's about limiting access to information to parties involved and the trusted party. The public can see someone is sending an amount to someone else, but without information linking the transaction to anyone. So this is where a public key comes in.
Yeah.
No one knows what Arpit's public key is. I can choose to keep it private. I can, like, no one needs to know who owns this particular public key.
Yeah.
People would know that this is my Bitcoin, or rather, this is my public key, right? No one would be knowing that this is me who is doing that.
Mm.
People would know this public key transferred to this public key. But you would say, Arre, Arpit, but you just shared your public key with someone, right? But think about it. For every transaction, I can create a new public private key pair. So that is where the Bitcoin network does not restrict us to not have multiple pairs of public key and private key. You can have as many public keys, as many private keys generated for you. You
Yeah.
can use, and it recommends you to use one for every transaction.
Mm.
If the owner of the key is revealed here, the risk is that if owner of the key is revealed, linking could reveal other transactions that belong to the same owner.
Yeah.
So for example, if someone knows your public key, they would know the exact amount of Bitcoin that you hold. But
Yeah.
if for every transaction, if you create a new public private key pair, see, so long as you own the private key, you own Bitcoin. As simple as that.
Yeah.
Right? So if for every transaction you create a new public private key pair and you use it, so long as you have private key for the corresponding public key, that particular Bitcoin that you have, because the Bitcoin belongs to what? To a public key. Right? To that particular Bitcoin belongs to. If you have the private key, you are the owner of that particular Bitcoin amount.
Yeah.
Right? This
Yeah.
is the beauty of it. So this is where it's saying that you don't have to use the same public key for every transaction. You can keep
Mm.
rotating a public key as granular as for every transaction, create a new pair and give that new pair or give that new public key to the person who you'd want to receive money from.
Yeah.
This is the power of, rather, this is the beauty of cryptography, right?
Yeah.
Because it is infeasible. Impossible to it's very shrewd word, but
Yeah.
it's infeasible, exhaustively infeasible for someone to guess a public private key combination, that it becomes very difficult for someone to regenerate and turn out that and basically start to be fraudulent in it, saying that, hey,
Mm.
no, this is me.
Yeah.
It's not going to that happen. And that is where here it says that if you keep the same public key, it's easy because it's a public ledger. People know which public keys sent how many bitcoins to which other public key. They know all the information. So if you keep your public key same, people would be able to trace that.
Yeah.
And this is where it so beautifully puts in the fact that, and it recommends you to do that for each transaction to keep them being linked to the common owner. Some linking is still unavoidable, but it promotes you to create a new public key
New
for every
public
transaction. But
pairs.
people
Yeah.
don't do that, but it's recommended to do that.
Yeah. It's
And
it's
this is
like
about privacy.
it's recommended to change your passwords more often. People won't do it, but it's recommended, right? So it's the it's the
Yeah,
same thing. They
yeah,
end up
yeah,
having date of birth as their password, but um,
yep,
so yeah, I think that makes a lot of sense. So it's at the same time, it's there is a lot of privacy because no one can trace back using your public key that who
yeah,
owns how many bitcoins. But it's also transparent that someone transferred these many bitcoins to someone, but that someone isn't known or publicly
yeah,
available. So that is the beauty. So it's transparent yet privacy is maintained, and then there is no central owner of the network. Everyone owns a bit, and they can remove themselves from the network, they can rejoin, they can regenerate the entire chain, they can download it, they can fill in the gaps by if there is some packet loss that you don't receive some blocks, you can still get the list of blocks that are not with you, and you can complete the chain. And then fraudulent is again, because it's so expensive to do that, no one would actually do that. So I think this paper is really nicely put, although there is a little ambiguity here and there, because I think it's intentionally that they don't go really deep into certain topics, because this is meant to be like an abstract overview of what they want to propose and not the implementation.
Yeah.
For example, I don't think they recommend what kind of hashing algorithm should be used or something like that. And that I don't know exactly. I haven't dived deep into that, like what kind of hashing algorithm is used and who governs that. So I think SHA-256 was mentioned as an example, but I don't know if that is used or not. The other thing which I found not mentioned here is the limit on the number of bitcoins. So we say that 21 million is the limit, and I was curious to read more about it. So I figured there are two theories around it, like why there is this limit of 21 million. One is purely like a theory, which is when this paper was released in 2008. The Satoshi Nakamoto, the group or the person, wanted to replace the fiat currency with Bitcoin. And at that time, US economy was 21 trillion, and that he calculated to be mapping to 21 million coins, which will be equivalent to 21 trillion, which can replace the entire US economy with Bitcoin.
Hmm.
And the second theory was uh, to so this entire mining process is dependent on incentives. So unless people get some incentives by mining, they
Hmm.
won't do it. And
Correct.
so the way they have put it is, uh, every 4 years, the incentive that miners would get would become half.
Yeah.
So when I think in 2008, for every
50.
new coin, you will get like 52 coins or something,
Yeah.
and then every 4 years it gets half. So they calculated this, that when it will become zero, so the
Yeah.
incentives would just become zero. And I think that's when it becomes
Yes.
transaction fee less, or
Yeah.
inflation safe and all that. But yeah, that is two theories, but it's not mentioned here. And the other thing I did not find here is about, so let's say I have a group of nodes, I try to do a fraud. There's
Hmm.
no auto mechanism where someone in the network can say, okay, these nodes are fraud because they have tried to change the chain or something like that. It's just it's not there. So maybe it's currently in the network that majority of the nodes think that, okay, these are the nodes that are fraud, and let's
Hmm.
not deal with them or throw them away of the network or something like that. But it's not mentioned here. But yeah, overall it's uh, really dense,
Yes.
really deep, and so many different concepts, moving away from trust based to proof of work. Got reminded of the childhood where we used to do this homework. So you have to do homework, and only then you will get like a sweet or a chocolate. So that's, you have to
Yeah.
prove that you have worked for it, and then you get the incentive. No one would trust you that, oh, I will do my homework, just give me the chocolate. So it's not that way.
True.
So I find that analogy here. Um, great. Anything you think would make sense to add more?
With respect to Bitcoin, there are a bunch of things that specifically, if in case people are trading, you literally don't own a Bitcoin if you don't have your public private keys.
Yeah,
So if you are just trading it, most people think that we own Bitcoin. No, it's the broker that you are using that owns the Bitcoin. This paper tells us that here it is written, a new key pair should be used for each transactions to keep them from being linked to the common owner. We just simply trade on the platforms. We
yeah,
don't even own Bitcoin. We think we own it, but we don't. The things are owned by the broker, not us. Right? So
yeah,
that is one really important thing, that you think you own Bitcoin. In reality, you don't, unless the Bitcoin, the transaction is noted in the public ledger that hey, you as your private is your basic public key owns that particular Bitcoin. Otherwise, you
Yeah.
don't own it.
Yeah, that's again like a trust based model on top of proof of
Yeah,
work. So the proof of work is being done by the exchange or the broker. And then you trust the broker that, okay, if they are saying you own this much Bitcoin because you are giving them your money, that's
correct.
you trusting them. You
Yeah,
don't own the, like, you are not the real owner of the Bitcoin, but they
correct.
are. But
Yeah.
you trust them that they will give you the money back. So
Yes.
that's
Yes.
that's again
Yes.
uh, so you get some convenience there because you don't have to write code, you don't have to generate public private keys. um, but
You're
yeah,
simply
there's
trading.
this.
You're simply
Yeah,
trading bitcoins.
trading. Yeah,
Yeah. So, which is where people need to understand the difference between trading and owning. Here, your broker is saying that you own these many bitcoins. This does not mean you really
yeah,
own it. You are building the trust with the broker. That if broker says I own it, then I own it. If broker changes its database and says no, no,
yeah,
no, now you don't own it. So now this broker is kind of a bank there. But obviously, there are a lot of things that have changed in the broking side as well to build more trust and more transparency. So they are also
yeah.
taking actions to establish that. But we are engineers. We like diving deep into the engineering aspects of it and appreciate the beauty and how this paper literally discovers, like solves, like define a problem statement, finds a solution to one, immediately tackles the next problem, then discovers another problem, and then it tackles it, then another problem, then it tackles it. So yeah,
Yeah,
that's the
absolutely.
beauty of this paper.
Yeah, absolutely. And this is basically so Bitcoin is basically nothing but a value created by your CPU power. So you
Yeah.
just spend a lot of CPU power, and that power gets converted into certain value, which is the coin, and then you can do certain transactions, uh, doing the same process again and again. So yeah, it makes a lot of sense. And since this paper is like old, like 2008, I'm sure that there are tons of things added newly in the Bitcoin network. There's a extended Bitcoin network as well, where you have a lot of miners and wallets and all that. So but this is mainly from the technical standpoint. uh, it adds a lot of interesting details, a lot of important concepts, even in distributed systems. Uh, so yeah, I really hope our viewers will get a lot of insights and also a way to approach white papers. So if you have to add three things or three recommendations out of the entire discussion that we had
Hmm.
on reading white papers,
Hmm.
what would be those?
You have to read a paper at least thrice to understand it because it
Yeah,
took me 7 to 8 iterations on this paper to understand it fully. Because here they
yeah,
just in one line they mention thing, and this is how to, because white papers have to be pretty small. Like the research papers have to be pretty small, 3 page, 4 page, 9 page, 12 page, 13 page is a big one. Right?
yeah.
People like to keep it really dense because they expect you to know a lot of stuff. So you have to learn to read between the lines. So read multiple times, learn to read between the lines, and at every step, try to at every line try to understand the meaning of it. In
Mm,
first
yeah,
iteration, you would typically form a lot of discrete dots in your head. Second time when you read it, some of the dots would connect, some of the dots would become bigger and dense that you know this part really well. And then when you read the
yeah,
third time, then a good set of solid connections would form in your head. So depending on your grasping power, you would need 3, 4, 5, 6 iterations. But over time, these iterations would diminish, just like your Bitcoin
yeah,
returns. Right?
yeah.
You would get fewer and fewer, you will need fewer and fewer efforts to read a
Mm,
paper. Right? So read multiple times is the key. Form notes, read between the lines, and then try to make sense out of every single thing because it's hard to read paper, but it is very essential to get deeper understanding of the system, the tool, the framework, whatever we are reading.
yeah. Yeah, yeah. And I think one point that you mentioned earlier when we started this episode, it's not meant for spoon feeding.
Hmm.
It's giving you some information, but with an intention to make you curious, and they don't expect you to just get like, okay, I understand completely what how Bitcoin works now, but they
Hmm.
expect you to research more on that. There's a lot of other works. There are books written on Bitcoin on the same paper that they describe it in detail, like we are doing it in our
Hmm.
podcast. Like this is our interpretation of this white paper. So many people have done that. So it's up to us when we read a white paper.
Yeah.
You don't have to so I personally don't have the motivation to complete or the finished reading a white paper, but I have the motivation to absorb the knowledge. Even if I don't finish it, if I even if I just read two papers, if I'm getting a good knowledge, that is enough for me. So I don't rush finishing that. And as you said, if you are iterating like 7 times reading this white paper, which is 8 page long, I think it tells you that how much dense the white
Yeah.
papers are, and rushing through it does not make any sense. So give enough time to yourself. There's no rush. Probe into it. Don't take things for granted. Just go for it. Find more details and solidify the knowledge. So yes, as I initially said, we will tell you how you can become rich by using Bitcoin, but I'm sure you will become rich, at least in the sense of knowledge that you have in Bitcoin and the technology behind it. So yeah, thanks a lot, Arpit, for doing this. I'm sure it will add a lot of value for our viewers. And for our viewers, please, if you like the episode, please hit the like button, share it with your network, and not the Bitcoin network. Share it with your network, and also subscribe to the channel. So yeah, thank you so much, Arpit.
Thanks so much, KV, for having me. It was fun.
Awesome.